All right, let's talk about the Euler phi function. So, first of all, this equality here, um, I'll just write it out. Note that the equality nk over k equals n over nk follows from the fact that n is greater than or equal to 0, and, well, could I have order 0? No. Because the order is like the great. Obviously, anything raised to the power of 0 is just 0. It follows from the fact that n is greater than 0, and LCM of nk times GCD of nk equals the norm of nk. And so this equality, this is just a standard fact, and you can, they might prove this like in the, I didn't read through chapter 0 of this textbook, but I wouldn't be surprised if they proved it in chapter 0. And if they didn't, then go find this online somewhere or derive it yourself. It's a pretty standard fact about LCMs and GCD, by the way. This is LCM, this is GCD. So, let's assume, without loss of generality, that k is greater than or equal to 0, because it doesn't really change anything in this problem. See here. So now what do? We want to show that g to the k has order of this thing here. So n divides nk by definition because the thing on the right is just the least common multiple. So it's a multiple of n, so n must divide it. So if writing nk, this LCM, as an for some constant multiple a, because it's a LCM of nk is a multiple of n, so you just put some integer a here, and this yields. Actually, do we need to assume that k is greater than or equal to 0? I don't think so. I'm gonna. Ooh. I didn't mean to do that. But now that I've started, let's do it completely. So I'll write it back in if I need it, but I don't really think I need it. Let's see here. If you assume that late, you know I don't quite. I feel like all this LCM GCD stuff, it doesn't really. You can think of it as all being positive number. So let's just assume that k is greater than or equal to 0. Because if k is... Because obviously, show that the number of generators is the number of positive integers which are relatively prime to n. So, yeah. So we're just gonna take k to be positive. Does it really even make sense? Oh, well, right, because let's assume. Okay, here's how we do it. Without loss of generality, that k is greater than or equal to 0, because g of the k is going to be a subgroup. Oh, well, wait, that's true. This is not necessarily. Oh, well, the fact that the order of g is n, this is assuming that n is a finite number. And so if you're raising g to a negative power, you can always just convert that to a positive power because basically the group generated by gk is going to be a subset of the group generated by g, and the order of this group, or the subgroup, which is generated by G, and well, which is a group, but whatever. And this order is less than infinity. Well, it's equal to n, which is less than infinity, because otherwise these equations don't even make sense. And so, with that being said, there's only finitely many to choose from. And so if you have g to the minus k, then it must be equal to, g to the minus k must be equal to g to the m for some m between 0 and n. Well, one of these can be strict, but it doesn't matter. So yeah, for that reason, we can just assume that k is positive. Okay, so there we go. Anyways, after that tangent, so writing nk as some integer multiple of n, and of course now we know a to be positive, but that doesn't really matter. This yields, so we take this element g to the k and we raise it. First, we want to know that g to the k raised to this power of LCM nk over k. But what is that? That's just an divided by k. We want to show that this is 1. So what does this give us? The two k's cancel, and so this is g to the n to the power of a. But that's just 1 to the a, which is just 1. Okay, so now that we know that this exponent that this is an exponent such that raising g to the k to this exponent yields 1, we want to prove that this is the smallest such positive number. So let's see here. Now suppose we have some smaller number, some smaller strictly positive number, some s that's between 0, strictly between 0 and LCM and k over k. Then if you take this part of this inequality and multiply by k, we get sk is less than the LCM of nk. But this is the least common multiple of n and k. So if it's the least common multiple, then that means that if sk is less than the least common multiple, then it can't be a common multiple. So it's either either n is not going to divide ks, or k is not going to divide as, or k is not going to divide sk. One of these two is going to be the case, because otherwise it would be a lower common multiple than the LCM, which contradicts the definition of the LCM. So anyway, but we know obviously k divides sk because sk is a multiple of k. So it must be that n does not divide sk. So if we write sk as n, if we do division, write sk as nx plus y, where y is strictly between 0 and n. No. Can be equal to 0, but it cannot be n. Then we have g to the k to the power of s. Remember, s is what we're trying to prove is not we want to prove that this thing is not 0, because s is less than this this LCM nk over k. So anyways, what is this? G to the ks is equal to, well, g to the nx times g to the y, But g to the nx is just g to the n to the x, and g to the n is 1, so this is just 1 to the x, and that's going to be 1, and so this is just g to the y. But because y is strictly less than n, which is the order of g, this cannot be equal to 1. So hence, order of g is equal to, and choose k over k, because no, order of g to the k is equal to LCM nk over k. And that's, of course, because g to the k raised to this power is 1, and g to the k raised to any lower power is not 1. So it's the smallest positive number such that g to the k raised to this power is 1. So there we have it. And so then the rest of it is pretty straightforward. So hence, let's see if I can, okay, so now the order, the next thing we want to prove that the number of element, we want to prove that the number of generators of g is the number of positive integers less than n, which are relatively prime to n. This should be pretty straightforward, or pretty clear at this point why it should be the case, but let's just write it out. And I think I'm going to write it out in a way that takes a little more time than necessary, but I don't know, I like doing this. So what we're looking for is the number of elements h in the subgroup generated by g such that the group generated by h is precisely the group generated by g, because h is such an element of the cyclic group generated by g, or the group generated by g, precisely if h is a generator of this cyclic group. So this is exactly the thing that we're looking for. But any element, okay, so now any such element h is going to be, we could write it as g to the k. G, so that g to the k equals g. Okay, that's not doing much. And so now, well, the number of such g to the k, we can just count it by the number of k's. Because we have a 1-to-1 correspondence between the g to the k's and the k's. This is, of course, we're considering here k between 0, well, not strictly. K can equal 0 through n, but it's obviously not going to be equal to 0 unless g is 1. Well, in which case, yeah, whatever. So so k is going to range from 1 to n, which is the order of g. So that's kind of implicit. I'm not writing that out because I'm already writing out more than I need to here. But anyway, so we have k such that the order of g, the k, is equal to the order of g. But then, of course, this is the k such that this thing is, we use the other form. Here, we have n over n to the k for the order of g to the k. That was our formula from the problem statement. And then the order of g is just n. And so, of course, we're considering k's which are less than n. And so, when is this true? This is true precisely when this this GCD nk is 1. So k such that nk GCD equals 1 as desired. That's exactly what we want to prove, that the number of generators of this G, of this subgroup generated by G, is precisely the number of integer, or the number of positive integers k less than n, such that the GCD of n and k is 1. And so there we go. This completes, this completes the proof.